Good morning, everyone. My name is Larissa Montaz, and I'm here to talk about research in the Beach Exposure and Child Health Study. Do you all remember back in April 24th, 2010, when the Deepwater Horizon oil well exploded, resulting in the death of 11 platform workers and one of the largest oil spills in U.S. history, with impacts to the marine and coastal environment that have yet to be fully understood? During the time of the oil spill, there was considerable uncertainty regarding the health risks associated with the oil spill, especially for children who are more vulnerable. Uncertainty also existed for the spread of oil spill chemicals in beach sand, water, and air. Fisheries and beaches were closed even in areas which were really far away from the edge of the plume. Crude oil are one of the most diverse and complex organic mixtures found in nature. They contain thousands of chemicals, with the most predominant ones being hydrocarbons. Now, it is important for us to understand the chemical composition of crude oil because each chemical or mixture of chemicals has a different effect on human health. The overall goal of the Beaches research study is to improve estimates of uncertainty in children's exposures and risks to their health due to oil spill chemical concentrations. Now you might ask yourselves, why are we looking at this in light of children? Well, scientific data indicate that children are more susceptible because they have proportionally more intake of chemicals. They have multiple routes of exposure, multiple pathways of exposure, and their activities as related to their social behavioral patterns make them more susceptible than adults. We plan to utilize historical data from prior oil spills to create, test, and validate algorithms that describe time-space specific concentrations of oil spill chemicals in beach sand, water, and air, especially in zones where children play. A third part of this project involves creating a risk assessment platform which utilizes the human activity and exposure side of the project in combination with the oil spill chemical distributions to create a risk assessment modeling platform which can guide beach closures in future oil spills. Statistical methods based upon Monte Carlo approaches for the confidence bounds will be utilized for the risk assessment. Now, how do we plan to do this? How will this be achieved? At this point in time, I am calculating or developing algorithms retrospectively. I am utilizing data generated by the National Oceanic and Atmospheric Association, NOAA, and its fate and transport model, NOAM, which was run on a daily basis from the 24th of April until August. I am processing this data in conjunction with sampling data from the EPA, the Environmental Protection Agency, which was sampled along the Gulf Coast throughout the oil spill. I have processed both data sets using GIS software and a Python script, and I have come up with time-space specific oil spill chemical distributions, which I generated retrospectively. Now, where do we go from here? As I mentioned before, the overall goal of this research project is to improve estimates of uncertainty and health risks to children due to oil spill chemicals. We plan to develop a risk assessment platform which may be used in future oil spills, and we plan to develop algorithms which can predict oil spill chemical concentrations in beach sand, water, and air, particularly in areas where children play. This final slide shows a cross-section of beach morphology. It shows the different areas at beaches where children play. And it also shows one of the example algorithms. This particular one is due to ingestion, as related to children's beach time play activities, oil spill chemical concentrations, and coming up with the dose of a particular chemical or an individual chemical for the raw oil. We hope to contribute to the body of knowledge in risk assessment for children to reduce future uncertainties to health risks in future oil spills. Thank you for your attention.
Okay, good morning. My name is Elizabeth Kelly. I'm going to speak with you today about enterococci and cyanobacteria in some local watersheds. I am a PhD student at the Abbott Center for Ecosystem Science and Policy. In the past, about over the course of the summer and before it's happened as well, there's been a state of emergency declared in 7 Florida counties. This has been due to the recent algae blooms, algae, of course, cyanobacteria. At the same time, in these same counties and beyond other areas in the state, there have been bacterial exceedances, particularly enterococci, a fecal indicator bacteria, reported at recreational beaches in these same counties and the others throughout the state. Why specifically is it that we are interested in cyanobacteria and enterococci? For cyanobacteria, this is something that can cause a public health risk. It can cause bacterial, it can cause irritations, respiratory irritation, headaches, sometimes some dizziness. With enterococci, it serves as an indicator for pathogens. These pathogens can cause GI distress and diarrhea and things like that. Where do these come from? Basically, for cyanobacteria and enterococci, they both come from being fed by nutrients. Generally, these nutrients are nitrogen and phosphorus. All right, let's go. Come on. Okay. How do we measure chlorophyll and enterococci? With cyanobacteria, you can measure this through the chlorophyll itself. It's a filtering method where you put it on the filter as you see here. You end up putting it into a spectrophotometer or fluorometer, and you see the fluorescence that comes back to see how much of the chlorophyll is present. For enterococci, you measure the bacteria by filtering it through water and filtering it through the filter there. And from there, you incubate it for 24 hours. After the 24 hours, you count the number of colony-forming units that are present in the filter. For this study, what we did was we chose 3 sites. The 2 sites, Roosevelt Bridge and Du Bois Park, are from the Florida Healthy Beaches program. These are monitored for enterococci specifically. We noticed them through a survey of all the beaches basically in the state that were measured, and these 2 happened to really stand out with their enterococci exceedances. With Roosevelt Bridge, it's also on the St. Lucie River, and that's an area that tends to have a lot of problems with cyanobacteria. We also chose, as a lot of times when people talk about why is it that these blooms are happening, they mention the releases of water from Lake Okeechobee. So we threw a Lake Okeechobee site in here as well to manage it. And so there's our Canal Point site, which just provided us with some background to see what was going on in the lake. At the same time, we're looking at the enterococci and cyanobacteria at Roosevelt Bridge and Du Bois Park. You notice also there is a spot where this shows the flow from the lake. C-44 is a man-made canal. This is not part of the river at all. It's been dug out. And then right around S-80, which is about 7 miles from Roosevelt Bridge, then it actually joins the St. Lucie River. So it's sometimes known as the C-44 S-80, but this is not the entire St. Lucie River. It only becomes right up at the top near where Roosevelt Bridge is. So in looking at all of these beaches, recreational areas, managed areas, we compared enterococci and chlorophyll to see if there was anything why these 2 are happening at the same time. Why do we have these exceedances at the same time in somewhat the same areas? At Du Bois Park, which is not an area known for algae exceedances, it's on the Loxahatchee River, and they don't have these same issues. Perhaps because there are no lake releases, but they both have phosphorus in common. Roosevelt Bridge didn't seem to show anything really enterococci, and we didn't really have a lot in common with the lake data. So this is what we have learned so far, and future work I hope to focus more on these that we have learned here.
Wonderful. Yeah, so I'm going to talk about the novel method that we recently developed to treat multidrug resistant bacteria in water. Oh, it doesn't work. Okay, so the motivation is that recently the CNN News and the CDC News, as you know that we have Hurricane Irma last year, Hurricane Harvey in Texas, and the flood water, when people contact in the flood water, there is a significant risk with the deadly bacteria mostly is a multidrug resistant bacteria present in water. So we are thinking about to develop a new method, alternative method to the conventional chlorine disinfection due to the potential issue with the conventional in terms of the cost effectiveness and the longevity of the effectiveness. So the hypothesis is that what if we make it nanomaterial that coated with biodegradable materials so that we can minimize the leaching issue of the nanomaterial in water. Second of all, if with the coating biodegradable material onto the certain types of especially metal oxide nanoparticles that have a high antibiotic bacteria resistant bacteria, so that we can have better control in terms of targeting the drug resistant bacteria. Now another hypothesis would be reactive oxygen species generation. So that with the release generation of reactive oxygen species, the nanomaterials from the aerosol generation can treat it and target particular types of bacteria in water. So the goal is to develop and advance new antimicrobial resistant bacteria, multi-drug resistant bacteria, especially to deal with difficult to treat contaminant of concern. So this is the alginate encapsulated zinc oxide. It's new antimicrobial materials. Without the zinc oxide nanomaterial coated on the bead, nothing happens. So no removal in water. But when we coated the zinc oxide, which is one of the material that has a high antibacterial resistant bacteria can easily remove the the bacteria present in water. So alginate encapsulated zinc oxide bead were successfully synthesized, and we saw that significant removal. Now people are confused with whether E. coli is a deadly bacteria, but there are many different types of bacteria present in water. So the E. coli that we used was DH5 alpha type, which is one of the antibiotic resistant bacteria, and also Pseudomonas aeruginosa. This is the one of the multi-drug resistant bacteria. So we found out that very interesting significant removal with only small amount of zinc oxide encapsulated in the alginate bead. The alginate is environmentally friendly biodegradable material. So in order to confirm the possible mechanism, so one of the hypotheses we came up is the release of reactive species. So what about if we minimize the aerosol generation? So we added the scavenger NAC. NAC is a scavenger of ROS. So adding the NAC, we found the significant inhibition of aerosol generation. So which confirm one of the primary mechanism responsible to treat the bacteria in water. So the future research direction is that we want to test it how reusable it is, the bead, how reusable the bead are, and the further application, is to optimize it, the treatment parameter better. So we are currently working on the company, collaborating with the company Jacobs CH2M, and this was supported by EPA, and my student working on this project. Thank you so much.
So good morning, everybody, and welcome to this presentation. Today I'm going to talk about how we go towards the full deployment of corrosion-free concrete structures. So how we, what is it? That's not it. Sorry. Thank you for that. Okay, so before starting with the presentation, let me set you a little bit in context. So please raise your hands, all those that suffer traffic delays here in Miami. So all of you, right? Don't be shy, come on. So mainly all these traffic delays are mainly caused by the repair work that takes place in our bridges and roads. So our bridges and roads are mainly made of a steel reinforced concrete, which is a steel reinforcement with concrete. What happens is that in areas such as Miami, where we are close to the water, this steel reinforcement gets corroded, leading to the deterioration of the whole infrastructure and leading to these repairs. And here in the US, per year, we have more than $22 billion cost in these repairs. So there are many other universities that are working, trying to reduce these delays. What we do here at the U, we always go one step further. So we just try to get the corrosion out of the equation. So how do we do it? Using another type of reinforcement, which is glass fiber reinforced composites. So as you can imagine, I mean, we cannot be here 100 years testing all these materials to check the durability of them. So we have to use some tricks, and in this case what we use is the accelerated aging. So we put all these materials, this reinforcement that is gonna replace steel, we put them in these magic chambers, what we call magic chambers, that are chambers, in our case they are filled of seawater and at high temperature. So we are gonna use three types of three temperatures, 23, 40 and 60 C, and we are gonna leave this material for 60, 120, 210 and 365 days. So after we leave the material for that time, these chambers at that high temperature are gonna kill the material. So what we need is we need to check the properties before and after this accelerated degradation. So we do a lot of testing. We do mechanical testing such as tensile tests, different shear tests, also bond to concrete, since it's a very important parameter. And we also go a little bit more fancy. We go also to the microstructure. We do SEM, which is scanning electron microscopy, and we check in the microstructure how that durability is affecting, how that degradation is affecting, and if there is a big difference between the pristine or the material that comes directly from the manufacturer and the material that it's aged. So afterwards, what we do is, so now we have the accelerated aging, now we have to come up with the relation with that accelerated aging to the real life. For that, we use some complex mathematical models, such as Arrhenius relationships, that relate that extra, like high deterioration to what does that mean in the real life. So what we saw out of this research, it's not completed, but we have a lot of data that we can take some preliminary conclusions. So until now, there's no deterioration, no major deterioration. So we are proving that the durability that this material, that we say that this material has, it's there. So we see that we have different materials, different manufacturers that produce different bars, and each of them have different properties, but all of them meet the durability standards. However, we are claiming that there is a need for the standardization of these materials, since it's going to be better for its commercialization. So, and here is the most important part of this project, that it has a great impact in our society, since right now this material, the Florida Department of Transportation, who is very interested and it's funding this project, they are not allowing to use this material in structures directly in contact with seawater because there is not enough research. However, they are funding this project since they want to see, after all these tests are done, if the durability is proven, then they will allow the use of this structure of this material in, for example, seawalls. As you can imagine, here in Florida, all the hundreds of miles that we have of seawalls, that we could have them corrosion-free by using this material. So this is the end of my presentation. Thanks so much, and please keep an eye on this technology, because when it goes, it's gonna go hard. So thank you so much.
Okay, I'm going to talk about the pozzolanicity of supplementary cementitious materials. Keeping on with the theme of concrete, a lot of people kind of say, concrete's really bad. It contributes 5 to 10% of man-made CO2 emissions, and that sounds like a truly dreadful number, and it is. But then you got to think about the fact that we use more of concrete than just about any other material, except for water. So if you actually look at the embodied energy data, cement is pretty low. Concrete is even lower, because concrete is only about 15% of cement or something. So this is an issue of scale. It's not that the concrete or the cement is bad in itself. However, we can still do better. And what we have been doing, cement scientists or concrete material scientists for the last 50 or so years, or a little bit longer than that, is we've been replacing cement with supplementary cementitious materials. These are typically waste aluminosilicate materials, which increase the concrete durability and sustainability. And a whole bunch of them look like this. The problem is we do not have enough supplementary cementitious materials. As you can imagine, finding a billion tons of materials, no, several billion tons of materials every year is not that easy. So we have shortages both locally and globally. This means that we must identify novel supplementary cementitious materials. Problem with doing that, and I could talk for hours and hours about this, but the standard tests for doing this are actually extremely inaccurate. They do not measure any sort of fundamental behavior. They just, they're from like 30 or 40 years ago, and they're dumb. Let me just put it that way. So we need to develop new, better test methods. So what we've been doing is actually, we try to study the fundamental process of what's happening. That fundamental process is simply that supplementary cementitious materials react with calcium hydroxide. Calcium hydroxide is not good for the concrete. That reaction produces calcium silicate hydrate, which is good for the concrete. So if a supplementary cementitious material is reacting with calcium hydroxide, that's a good indicator that it's good for the concrete. So we have to identify this reaction. So what we do is we have a model system of supplementary cementitious materials, calcium hydroxide, crudely illustrated there. There's a couple of other variables. I do not get into the details of that. And essentially, we measure two things. The first thing is how much calcium hydroxide is consumed, and the second is how much heat is released. These are actually not identical for somewhat slightly complicated reasons, and those are the test methods that you use to do that. That second picture is from a while ago. Unfortunately, I'm not allowed in the lab anymore. So, well, I'm not allowed because my students get scared when I'm there standing behind them, but just kidding. So anyway, moving on to some of the results. So this is from about 50 different materials, including about 10 or 11 different classes of materials. And actually what we see is that this material classification system that we've developed, you actually get about 5 or 6 different classifications of these materials. You have highly pozzolanic, more hydraulic, pozzolanic. These are good materials. We want to use them in concrete. Interestingly enough, almost all the conventional SEMs that we tested fall in that category. Not very surprising. And then we have inert, which is really not doing very much, and less hydraulic. And these, for the most part, are not that effective as supplementary cementitious materials. We tested 3 new materials. One is fly ash coming from the burning of municipal waste. You can imagine that something like this is a material that's going to be very commonly available in the future. The other is a slag coming from the iron making industry. Both of these materials are from China. Unfortunately, they're really new materials, but they turn out to be not very useful. The third is a powder coming from grinding of lightweight aggregates, which is used very commonly in concrete. That one actually turns out to be pretty good. We don't have to worry about the individual classifications. The idea is that if you have something that's over x equals 60 and y equals 200, you probably have a really good material. Right now, we're actually looking at, depending on the classification, what sort of replacement level of cement and concrete can we use. There's actually quite some science into this as well. So we took all of those 50 materials, grouped them into 3 different types of materials depending on their chemical composition, and this is just the bulk chemical composition. So depending on their calcium, alumina, or silica content, you actually get very different slopes, and this seems to arise because of different reaction enthalpies. And this is really nice because then we only need to measure one of these 2 tests to actually get the other one. So the idea is we can actually predict fundamentally from the chemical composition the response. So to conclude, we propose a new test. This test seems to work really nicely so far. The relationship seems to depend on the chemical composition, and in the future we look to study more new materials as well. Thank you very much. If you want to talk about cement or concrete, shoot me an email, catch me in my office. Thank you.
Thank you very much.
Well, my name is Caitlin Kozar. I'm a PhD student under Dr. Garamani. My topic is a bio-inspired approach to sustainable concrete. Basically, bio-inspired materials are actually already in the industry. They're actually spread out over various fields. Here are just a couple examples. We have gecko feet that are actually influencing the different tapes because of their adhesive qualities. Even in design, they're designed in trains or blades, and this is actually a medical material. So right now I'm focusing on 3 common proteins. These are actually very well-researched proteins. Albumin and lysine are both used in food products. Actually, you've probably eaten them today. And hemoglobin, as you know, is actually found in blood. The reason we chose these is not only are they well-researched and their properties known, is that we were able to test their foaming properties in an alkaline solution. Now, cement is very high pH. It is not very well suited for living situations for these proteins. So we focused on the actual foaming abilities. So basically, we did various tests. Oh, wow, totally missed that. Anyway, we put these into cement to test their changes that they actually made in the cement. For albumin, we actually saw a high increase in the air content. As you can see, it actually went up to 6.5%, which is far greater than a normal cement time. It also basically increased the setting time and decreased the flowability, which actually allowed the air voids made to remain trapped in the cement. Hemoglobin actually was very similar. It had a very high foaming ability, but a very low air content because the flowing was so high and the setting time was over 30 hours that actually all the air was able to escape. Lysozyme, you can actually see this little middle area where the larger air voids joined together and actually rose to the top, but were actually stuck before the setting time allowed them to rise fully to the surface. Here you can see them in the proteins in the alkaline environment, where it actually lines up fairly decently with the stability capacity of the proteins. So we tested basic tests in these alkaline environments that are well known in distilled water and other materials, and compared them to our results in cement. We're currently working on analyzing the results and finding connections in how we can continue this and test other proteins and test other synthetic polymers and other modifiers in order to eventually work on creating our own bio-inspired admixture based on proteins as a building block. So yeah, that's about it.
Good morning, everyone, and welcome to this presentation. My name is Babak. My advisor is Dr. Ali G. So I'm going to talk about the use of the hydrogels to improve the sustainability of the concrete. So most of you know that the concrete is widely used material in construction, but one of the problems with the concrete is cracking, which is endanger the durability of the concrete because it generates a pathway for harmful materials such as sulfates and also salts, which is cause corrosion. Okay, we have different type of the cracks. I'm not going to talk about all of them. Some of them happen before the hardening of the concrete, and some of them happen after the hardening the concrete. So what I want to look for is the autogenous shrinkage of the concrete, which is the lose of the water from the paste to allow hydration in the mix with low water to cement ratio material. Okay, so the idea is here that because we lose the water from the paste in the concrete, we will have crack, but we have to do something to keep the water into the system. So the idea here is that we have to use there's a material which is called super absorbent polymer, SAP. You know, the commercial one is used in the baby diaper. It has the ability to keep the water inside, absorb it, keep it, and also release it over the time so that we can control the shrinkage. So this is my result. I have already used the two different kind of the SAP. As you can see in the first graph, the amount of the autogenous shrinkage is mitigated using the hydrogel. But the problem with the hydrogel is that the compressive strength reduces because it left some voids inside the paste. Thank you so much for your attention.
So good morning, everyone. I'll be talking about the enhancement of the coastal resilience in terms of our structures in our cities. So this is all about collaborative design and the multiple projects with multiple experts. So before we start, I want to put you in the context. So what do we define as coastal resilience? And coastal resilience is something which is well defined. If you search around, this is the definition by NOAA. So it's the ability of the community to bounce back after a disaster. The disaster could be man-made. In this case, we're talking about hurricanes, coastal storms, and flooding and other events. So it's not just reacting to an event, it's how we get back. So there's a component of time, and there are multiple, let's say, perspectives on that. Now, because there are multiple perspectives, we have to address this complex problem through a collaborative design approach. So collaborative design, again, is not an abstract concept. It has been studied and well-defined in literature, and one of them is Kwan, who defines it as parallel expert actions. That's great. This is something we all do. They have a short duration, that's relative, they can be long or short, but what I want to focus on is the last part where we are bracketed by joint activity of negotiation and evaluation. So if you ever worked in teams and if you collaborate, I'm sure you had interesting negotiations and evaluations throughout your projects. So I'm going to show you a series of projects where this happens all the time. The first project is with the School of Architecture. So we have worked on a resiliency and preservation information pamphlet. There we talk about how we can actually prepare, defend, adapt, mitigate, and relocate or rebuild existing structures. And this is in order to avoid effects such as what you see on the right side of the slide, where these are pictures taken after Hurricane Irma down at the Keys. You can see that there are structures that had limited impact, and there are structures that were unfortunately devastated by either the wind or the storm surge. So wind and storm surge are the two key loads when we're talking about hurricanes, especially in coastal regions. And this is actually what we're studying in another collaborative project with Rasmus and Brian House at the SUSTAIN facility. So the SUSTAIN is the surge structure atmosphere interaction facility. We simulate wind and wave action, and we can come out with the load with different time series so that we can test the structures and understand also the interaction between wind and wave under a hurricane. So we want to study the loads so we can enforce our structures, but in order to enhance the coastal resilience, we can also protect our structures. And to protect our structures, we can work on multiple fronts. One of those, which relates to a talk given previously by Alvaro, who is talking about the composite materials, is this project that just came in. So this is going to be a project about a eco-friendly or biocompatible, modular, efficient seawall design. So in this project, we collaborated with Dr. Nani here, as well as Brian House, to get the efficiency there. But we also work with ecologists who guarantee that we ensure that biocompatibility, not only in terms of the material, but also in terms of the shape and the structural complexity of this design. Now, another project is through the ULINK project. So this is the Laboratory of Integrated Knowledge, and this is something that's studied in our school. And in this project, what we're doing, we're studying the effect of corals in the wave energy dissipation. So what we're doing there is we're working with ecologists who are focusing on coral restoration to see how the corals can be used to actually enhance our coastal resilience. So how they can protect us from the waves. So we make some measurements of the waves before and the waves after a coral reef, and we estimate what would be the wave energy dissipation, which are the key parameters that determine that, and how we could enhance that with structures. And lastly, when we go to the state to the scale of a city, then there are multiple parameters there. So at the city level, we cannot act only on the engineering. We have to take into account the urban design. We have to take into account the social science, and that is hidden within a city. So a city is a living organism, and it has a social character. So what we're doing there, we study the infrastructure networks using graph models in order to understand their behavior under damage and quantify their performance throughout and integrate those social aspects through our models. Thank you. So good morning, everyone. So this is my second talk, and they gave it back to back to me, and this is a little bit about my passion, and it's about tensegrity, a system that has been used from art into science and engineering. And this is basically, if you're familiar with art, you might have seen those sculptures out there. So these are sculptures by Kenneth Nelson, who passed away recently. And so Kenneth Nelson worked with cables and struts. He puts them together, he finds a stable equilibrium, and these struts float in the air. This is an interesting and intriguing concept for engineers. So directly when he did that, he was working with Buckminster Fuller. Buckminster Fuller is a well-known, I would say, architect, engineer, and he was a multi-dimensional personality. So he came up with the word tensegrity, tension and integrity, which then was used into multiple, let's say, other projects. So tensegrity has since gone from art into science, starting from mathematics. It went also from art directly to architecture. So architects have been proposing tensegrity structures due to their aesthetics. So you see here, this is the Blur building that was a temporary construction in a lake that looked like a cloud in the lake, but actually was, it had that, I would say, skeleton, which was a tensegrity structure. If the architects used it, we have to guarantee its stability, and engineers directly jumped in. Civil engineers saw that we can span we can have long spans. So this is a tensegrity roof, again in Switzerland. It's the World Cycling Center. It has a tensegrity roof, and it's a very interesting and aesthetically pleasing structure. So we have to guarantee the stability of this thing. But beyond that, it has been used in science. So Dr. Imberg, who visited our school a couple of years ago, if I'm not mistaken, has been using that for the modeling of the cell, the cytoskeletal mechanism, in order to simulate the combination of the mechanisms with respect to the structure of the cell. And of course, NASA jumped in also because these are robust structures. So NASA presented this ball-bot, the super ball-bot, which is basically a tensegrity structure that they came up, which has actuators in the struts, so it can change the length of those elements, and by changing the length, we can make it move. So they proposed this design for planetary landing and exploration. So before we send anything to space or we put it in our buildings, we have to guarantee that it's stable, that it works, understand its performance, not only in the short term, in the long term, but also under damage. So this is what we are doing here. So we are focusing on the generative design, so how we can have these structures designed and get the desired properties that we want. So we want to control their shape, we want to control their behavior, and we want to also inform their assembly. Their assembly, although it looks elementary, it's a big problem because typically the stability is not guaranteed unless you have all the elements in place. So what we're using, again, we use a little bit of math, so we use rigidity theory and graph theory, and we are inspired, like the previous talks, from nature, so we use the mechanisms of adhesion and cellular fusion, so we're putting things together and they stay together as independent organisms, or they're fusion together, and by doing that we can create complex structures. So this is basically the composition of the module that you see on the right. The module on the right is the one that NASA have been using, and this is the composition by different units, we call them cells, of that model. So what we're doing is we're adding cells and we're removing elements throughout. So throughout this process, our structure, which is on the left side, is always stable. So we don't need to have temporary supports or anything, and it can guarantee also taking some loads if needed. So we can compose that structure, and we can also understand the behavior of the structure on the right by understanding how it is composed from the structures on the left. So this is the end result. So this is pretty basic, but then when you're using a method, you have also to show that you can do interesting stuff and more complicated stuff. So we came up with a Stanford bunny, which is a benchmark problem in computer graphics. So we polygonized the bunny and we did different resolutions, as we call them, of the tensegrity. So this is the class 1, so the bars are not touching, but we also did some other versions of it. So this is another low resolution version, and of course something that I will ask my students to build, the high resolution. Thank you.
So, good morning everyone. I am Haluk Damgacıoğlu. I am a PhD student in the Department of Industrial Engineering. I am working under the advisor of Dr. Nurçin Çelik. And besides sustenance and the sheltering, the electricity is the third most important thing in our lives in today's world. And our research mainly focuses on how we can make the electricity available to all the people and all the times. Unfortunately, our current electricity system still allows some power outages and disruptions. For example, especially in the natural disaster. For example, after the Hurricane Irma, the 80% of the Miami-Dade County was left without power, and nearly a week after, 25 of the accounts were still in the dark. So this happens also in the Hollywood Hills Rehabilitation Center, and the center lost its power during Irma and within days, and unfortunately 11 people died because of the power outages. So, and apart from this tragedy, these power outages and interruptions can cost billions of dollars on the US economy based on the Department of Energy. So then after the tragedy, the people start to buy generators. However, the generators can break down. They need to ramp up time to produce enough power and work efficiently. And they have also important drawbacks on the resupply of raw materials. So therefore, the generators are not reliable or resilient solution or our needs. On the other hand, microgrids promises energy independence and more energy resilient solutions for our future and today's world. Basically, microgrids are a localized group of distributed energy resources, including renewables and diesel generators, energy storage units, and controllable loads. So this concept allows us to control both the generation and demand simultaneously. So this is our main framework to operate the resilient microgrid and design a microgrid. So basically we collect the data from the microgrid from the real system, and we first run the low fidelity simulation. The low fidelity simulation allows us to assess the system on real time. Because if you want to focus on high fidelity simulation, only 1 second simulation takes minutes. So first, low fidelity simulation says that, okay, we have enough power or not. If we don't have enough power, we run the optimization model, high fidelity simulation, and design selection model to satisfy the critical demand in the microgrid system. So even we have an advanced technology on energy systems, still these devices, the components in the microgrids are not smart. For example, the PV arrays should be controlled to extract the maximum power, and we need to control the batteries considering the non-linear characteristics of the batteries. Here we also use the two battery system to increase the resilience and reliability of the system. And we also need to control we also need to regulate the voltage and current in the system. And we have also a user interface that we can monitor the system and we can control the loads. So we first implemented our framework on a proof of concept study in the emergency operating center in the city of Coral Gables. And this center includes the 911 system, and our results were very promising. So here we first determined the battery sizes and the solar PV panel sizes, and then we run the considered worst case scenario, which means that we have only one battery available, no solar panel, and no diesel generator. So here, with 80% of state of charge value for only one battery, we can provide continuous power for 911 system for 90 minutes. The 90 minutes is a requirement from the city of Coral Gables. And also, our system response time is very low in a second. So for example, after a power outage occurs, we can provide the continuous power after 0.15 seconds. So thank you for listening. If you have any questions, please let us know. We can happy to discuss with you. Thank you.